Hello everyone, welcome to our PBL Level 1 Physics project. Today we're going to talk about sound. What is sound and how do we create sound? Where do we use sound? What is the physics behind sound? And we're going to talk about some musical instruments and how do you actually have different musical instruments and what's the physics behind them. And that's what we're going to talk about. And in our experiment today, we're going to find the speed of sound. Can you imagine that? We're going to find the speed of sound. Actually, I was always wondering how you can find the speed of sound, but today we're going to see that it's very simple. All you need is a tuning fork and a ruler. That's it. All right, what is sound? Sound is a very simple definition. It's vibration of the air molecules. So what is air molecules? These are some scientific terms, but you don't need to get scared. It's just movement of the air. That's it. So we have a tuning fork. I know that you all have a one at home. As you can see now, it's vibrating. You can't really see that it's vibrating, but it actually does. Let me show you again. So sound is vibration of the air. So anything that is vibrating the air is going to create sound. Anything that vibrates, anything is going to make some sound. Some you're going to be able to hear, some you're not going to be able to hear because our ears are limited. We can't hear every sound. So music is another part of sound. When we are listening to music, we are hearing a lot of different notes, and they all part of our demonstration today. So we're going to talk about how they are made. For example, we have a very simple musical instrument over here. So it is only having 3 different metal bars, and that's it. But they all create really different sounds, and it's all about what is the difference in between those 3 metal tubes? The only difference is their lengths. That's it. So depending on their lengths, they're going to make different sounds because they're all going to vibrate the air with different frequency. Frequency? What is frequency? Well, it's a very simple definition. Again, frequency is a number of cycles in a second. So whenever I say that has a frequency of 500, then that means this is vibrating the air 500 times in a second. That's a lot, but believe it or not, that's what they do. So they are vibrating the air with like 500 times. So that's what an frequency is. So all of those instruments, well, depending on the type, they're going to create the sound depending on their frequencies. And the frequency in this case is going to be depending on the length. And it will depend on the metal that we are using. Of course, if you're talking about a guitar, then the note is going to depend on the thickness, this tension on the string, and the type of the string. So these are going to determine how we hear the sound. And today we're going to, in our experiment, we're going to find how we find the speed of sound. All right, our experiment is very simple. First, we're going to introduce our materials. We're going to need a Pasco tuning fork set from C, B, A, G, F, E, C, and O. And as you can see, these are our tuning forks, and they all have their frequencies written on them. We're going to need the tuning fork set, and as you can see, they all have different lengths. All right, we're going to need a meter stick to be able to measure the length of the harmonics, and we're going to need our resonance tube over here. And this resonance tube, again, is from Pasco, and you are able to create a closed-end tube, and that's a variable one, so you can make the length of the closed tube however you want. So that way you're going to be able to find the harmonics. And wherever you hear the clear sound, you're going to stop it, and then you're going to measure the distance from this end till the point. Okay, in our experiment, we're going to find the speed of the wave. And in our case, the wave is the sound. So basically, we're going to find the speed of sound, and it's equal to frequency times wavelength. And our frequency is going to be the frequency of the tuning forks that we have. And then we're going to have multiple tuning forks, and then we're going to create a sound. And then that's our frequency. But to be able to find the speed of the wave, it's frequency times lambda. But to be able to have a slope in the equation, you're going to need a number divided by another number. So we have our frequency. So if we divide frequency by 1 over lambda, then we again get frequency times lambda. Or you can have lambda over 1 over frequency. That's going to give you the same thing, but in our experiment, we're going to change the frequency, and we're going to find lambda values. Then we're going to find 1 over lambda later on. So basically, if you have the graph of frequency to 1 over lambda, the slope of this graph is going to be frequency over 1 over lambda, which is the speed of the wave. And in our case, this again, our wave is the sound. So at the end of the experiment, we're going to find the speed of sound. All right, we talked about what we're going to do in the experiment. We know our frequencies. That's our tuning forks. And then we said we're going to need 1 over lambda. But first, we need to find lambda. All right, here we're going to explain how we're going to find lambda. So if we think about a sinusoidal wave, which is a sound wave, one full wavelength is going to be 1 up and 1 down, and then it's going to repeat the same motion. So that's 1 full wavelength. This is 1 full wavelength. And if you only have up part or down parts, then that's going to be half of the wavelength. And if you also cut this one in half, then you're going to have this portion of the wave. And this is basically quarter of the wavelength. And in our experiment setup, what we're going to have, one closed end and one open end. And in this setup, one end closed, one end open system, the shortest wavelength that we can fit in is this wavelength. And from here, you can also see that this is quarter of the wavelength. So this wavelength, this length is going to be quarter of the wavelength. So lambda over 4 equals to the length of this part. So my lambda is going to be 4 times length. In our experiment, what we're going to do, we have the tuning fork over here. So we're going to vibrate the tuning fork in this end. And with this piston, you can move it backward and forward. And we will try to find, this is when you hear, that's when you have a sound wave fit in, a quarter of the sound wave fit in this tube. So at this point, you're going to be able to hear the sound, and that's called a resonance and the first harmonic. So we will try to find the first harmonic by pushing this or pulling this piston backward and forward. So once we hear the sound, then we're going to stop there, and then we're going to measure this length. And like we discussed over here, this length is going to be quarter of the wavelength, and then our lambda, which is the wavelength, is going to be 4 times the length that we have. So that's the experiment. That's what we're going to do. And by collecting a couple of data, trying different tuning forks, and finding their lambdas, we're going to be able to find our table, and then we're going to find the slope of this table. All right, we're going to start our experiment with the lowest frequency, which is 256, and that's note C. And we're going to vibrate that, and then we're going to hold that in front of the tube, and then by moving this backward and forward, we will try to hear the first sound, which is going to be the first harmonic, and we're going to measure that distance. All right, let's start. All right, so we are trying to hear the sound. As you can see, somewhere over here, you see. So that's where we hear the most sound. And that's our first harmonic, and that's our length over 4. So we need to measure that distance. And let's measure that distance. from the ground to there, it's 34 centimeters. What we're going to do here is, on a computer, on the Excel, you can have a table. And over here, I put all of the frequencies that we're going to try in order. And then we're going to measure the lengths. And this length is not going to be the wavelength. And the measurement that we have is 34 centimeters. So we may have to make sure that that's in meters. So that's going to be 0.34 meters. And our wavelength is going to be 4 times of that, and then that's going to be 1 over wavelength. But first I'm going to measure all of the lengths, and at the end I'm going to calculate all of the wavelengths and 1 over the wavelength. So next we're going to move to next tuning port, which is 288. All right, again, the system is simple. That's where we hear the most sound. And let's measure that distance. And that is going to be 30.5. So that's going to be 0.3 over 305. And next is 320. We are trying 320. That's where we have it. And that is 27.5. So 0.275. And next, 341.3. And it is going to be 23. No. 25. And next is 384. Distance, and that is 22.5, 0. And next is 426.7. And that is 20.3, 20.5. And next one, 480. And then this is 18. And the last one. Is 16. All right, now we're done with our measurements. So we collected all of our data. And what we need is, we're going to find the wavelength, and then we discussed that the wavelength is going to be the 4 times of this length. So on the Excel sheet, we can have an equation. So you press enter and select the data that you want, and then multiply that with 4. So Excel is going to calculate this for us. And then if you double click that double corner, then it's going to measure all of the rest of the data for you. And then again, same method. We're going to need 1 over wavelength. This is the wavelength, but on the graph, you're going to need 1 over wavelength. So this is the 1 over wavelength part. So again, equal 1 divided by this measured data, and then press enter, and it's going to give you the wavelength. So if you double click on it, you're going to see that it's going to give you the 1 over wavelength. And if you want, you can make it less decimals after the last digit after the decimals. So I think that data is good enough. So after that, what we're going to do is we're going to go to our Pascal program to be able to draw this graph. And I'm going to need a table and graph, and no data is selected. So what we're going to do is we're going to select a measurement, and we're going to make our own data. And our first data point is going to be frequency. And it's going to be measured in hertz. And on the y-axis, we're going to have our new data again, user entered data. And this is going to be 1 over wavelength. And then the unit for this one is going to be 1 over meter. So you can simply go to the Excel, and you're going to need frequency. Copy this, go to your Pascal, and paste them over here. And then go to your capstone again, and 1 over wavelength. Copy all of the data, and paste them over here. And now we can sketch our graph. So we're going to select a measurement. On the x-axis, we need to have frequency. And on the y-axis, we need to have 1 over wavelength. And this is our sketch graph. And what we're going to need the best fit line for this graph. And we're going to need this linear. And this is going to give us our data. And as you can see, our slope is 322. And technically, speed of sound in the vacuum is 340. So, and our class right now is a little bit denser than that, so it's going to be a little bit slower because the humidity and the temperature in this room is really high right now. So it's really close. And it's really accurate data that we find over here, which is 322. That's the speed of sound in our room right now. And that's the end of our experiment. As we discussed in our experiment today and explain what sound is basically vibration of the air molecules. And in our experiment, we measure the speed of sound. And where do we use this sound, or where do we use this principle? So basically, speed of sound is depending on the medium, which is where the air is, where the sound is traveling through. So right now, air is our medium because
sound is a medium.
Right now our medium is air, but density of the air, temperature of the air is also changing how speed of the sound is. So why is that important? When you are actually recording, when you are setting your guitar, when you are finding the correct notes, then it's very important that you are measuring, you're making the measurements according to the environment that you have. So for the orchestras, wherever the orchestra is, it's very important that they are setting up they are tuning all of the instrument according to the medium wherever the orchestra is. So it's very important, as you can see, even really tiny differences in centimeters are making a lot of differences in frequencies, and that's also changing the wavelength of the wave. So it's really important that we are measuring the speed of the sound, and we are tuning our instruments according to the medium. And it's really important that we are making our measurements accurately, because even tiny distance changes are going to make a lot of frequency differences, and that's going to change the speed of light a lot. So that's what sound is, and that's the importance of the sounds. And thank you for watching. See you next time.